mentioned, my name is Hanhan, and currently I'm working as a senior manager of data science at Scotiabank. And today we are going to talk about how to generate synthetic tabular data with generative adversarial networks, also known as GANs. So if you guys have any question, feel free to write down your question or interrupt me. If you write down your question, I should be able to see your questions. So first of all, a little bit about me. Currently, till now, I have been working in data mining area 11 years now. Data mining is a large area that includes data engineering, data science, and all kinds of data-related work. More than 10 years ago, when I was still at school, I was working for 3 academic labs focusing on web mining, which was trying to extract a large amount of data from the internet. After school graduation, I joined Microsoft as a big data and machine learning engineer. And at Microsoft, that was my very first time to work with data scientists. At that time, the data scientists built their models on smaller data sets, which were around 2 gigabytes. And I need to implement their models on large data system. At that time, we were still using Hadoop, a big data system. And the big data I had to deal with was at least 3 TB per day of data. So later, after I left Microsoft, I joined the MasterCard Vancouver Fraud Detection Center. We built different machine learning solutions to build fraud detection products. After I left MasterCard, I joined the Connexus here in Toronto. It's a supply chain system. We build supply chain machine learning solutions for our clients. Now I have been working in Scotiabank, the 3rd largest bank in Canada. We deliver more than 2 years now. We deliver different kinds of banking machine learning solutions. So no matter which company or group I had been working in, there's one common topic that's important everywhere, which is data privacy and ethical AI. So recently, you might have seen this type of news on the internet. Now, as you know, because of deep fakes, now there are so many fake photos, fake videos of celebrities that are spreaded on the internet. The fake data in data science is also called as synthetic data. And there are so many research and studies that are talking about how to generate synthetic videos, text, or photos. But today, none of this type of synthetic data is in our topic. Today, we are going to focus on synthetic tabular data. And maybe most of you are similar to me that we are dealing with tabular data all the time. The tabular data looks like the example here, looks like a table. They can be stored in a database, data warehouse, big data system, CSV files, or Excel files. And there are so many benefits to use synthetic tabular data in different industries. So for example, in healthcare system, researchers sometimes use synthetic data to build their research models. In this way, they can protect the real patient's data. So for example, IBM Watson Healthcare, when they were using they use synthetic data to build their cancer treatment model. So in this way, they don't need to disclose the real patient's data and be able to protect the patient's privacy. At the same time, the banking industry is also widely using synthetic tabular data in order to protect the customer privacy. As you know that for all the banks, the top priorities is to protect the customer privacy and data security. Synthetic tabular data had been used in different use cases in lots of banks. So for example, JP Morgan Chase, they used to use synthetic data to train their machine learning models in order to detect fraudulent transactions. And the Bank of America also use synthetic data to simulate customer behaviors in order to be able to personalize their banking services. Wells Fargo also uses synthetic data to simulate customer interactions so that they hope to improve the effectiveness of marketing campaigns and customer relationship management. So there are many use cases in different banks that are applying synthetic tabular data. Besides data privacy, synthetic tabular data can also be used in supply chain optimization. So for example, SAP, they use synthetic data to simulate the supply chain processes. In this way, they will be able to optimize their logistics, production schedules, and inventory management. So in a word, in different industries, there are a lot of benefits to use synthetic data. And most of the reasons it can protect the data privacy. And today, here is today's agenda. So first of all, I'm going to talk about the fundamental architecture of GANs. This type of traditional GAN, they are majorly used to generate images and text synthetic data. But by understanding their fundamental architecture, it can help us understand how does tabular GANs work later. Because no matter how complex GANs will be developed, the architecture is often built upon this fundamental architecture. And after I talked about the fundamentals, I'll introduce three latest tabular GANs to show how they are, how do they work to generate the tabular data. And at the end, I'm going to show you some experiments and findings to use these tabular GANs. So now let's start with DC GAN. So DC GAN is like the vanilla version of all the GANs. So it creates the most fundamental architecture. And later, a lot of GANs had built their architecture upon this fundamental structure. And the way DC GAN works is like the interaction between the criminal and the police. So when the criminal is trying to generate the fake diamond, the police is able to tell the real diamond. However, through their interactions, gradually the criminal is able to tell how to create the fake diamonds that look similar to the real diamond. So finally, even the police won't be able to tell what is the real diamond and what is the fake diamond. If we translate this process into neural network architecture, there are two major steps in DC GAN. The first step is to train discriminator. Discriminator in DC GAN is like the role of the police. It's trying to it's able to tell the fake data and the real data. So as you can see in this architecture, G here represents a generator. So the role of generator is similar to the criminal who's trying to create the fake data. So the generator gets noise data as data input, and then it will generate the fake data that's labeled as 0. At the same time, there's a set of real data set that's labeled as 1. In this step, both fake data and the real data gets into the discriminator to train the discriminator for classification. The classification is trying to tell the probability of the data to be real or not. So in this training process, the discriminator will update its parameters and output the probability to indicate the data set is real or not. Finally, these probabilities will be sent to the loss function to evaluate the model performance. And in the second step, is trying to train the generator. This step is called adversarial training. And in this step, the parameters in discriminator will be frozen, which means no matter what will happen, the discriminator will keep the same set of parameters. And the generator still gets the noise data as data input. At the same time, the generator is going to pass the gradients to the generator to train the generator. And when the generator updates its parameters, it generates the new set of fake data that's labeled as 1. And this new set of fake data will be sent to the discriminator to generate the probability to indicate how likely the data to be real. And finally, the probabilities will still be sent to the loss function to be evaluated. And these two steps, train discriminator and adversarial training, will be executed iteratively until at the end, the discriminator can no longer tell the difference between the real data and the fake data that's created by the generator. Till this time, we will use this well-trained generator to generate all the future synthetic data. So that's the whole process of how TGAN works. And after TGAN, there are more advanced GANs had been developed in order to overcome some weakness of TGAN or try to improve its capability. So for example, there's CGAN, which is also called as the conditional GAN. It allows you to control the output class. So for example, if you only use TGAN, then the criminal can only generate one type of diamond. But now with CGAN, if the criminal wants to generate a red diamond, he's able to get that. But if he wants to generate a green diamond, he can also do that. So CGAN allows you to control the output class. At the same time, all the GANs are notoriously hard to train, majorly because of gradient vanishing and the mode collapse. So for gradient vanishing, it's often caused because when the discriminator is confident about its classification performance, then it will stop updating its parameters. Therefore, the gradients sent to the generator will be too small, and the generator will fail to converge. So that's gradient vanishing. And for mode collapse, that's often because of the loss functions are not good enough, and therefore the generator often outputs the same output. For example, if the criminal wants to generate the red diamond, then he will get the red diamond. But when he wants to generate the green diamond, he will still get the red diamond. So the output looks the same. This is mode collapse. And in order to reduce the problem of mode collapse, algorithms like WGAN or ARS-GAN had been introduced in order to improve the loss function and therefore to prevent mode collapse from happening. At the same time, there are algorithms used to improve the perceptive output quality. Most of the time, they are used in improving output images quality. So for example, ARS-GAN is trying to improve the loss function and finally improve the output quality. For AC-GAN, it's trying to add the auxiliary estimator for the discriminator. By adding this extra estimator, the assumption behind it is it can improve the performance of discriminator and finally can improve the output quality from the generator. At the same time, there are some more complex GANs, such as disentangled representation GANs, such as info-GANs, stat GANs. This type of GANs allows you to control the output probabilities. For example, you can change the shape of your output. And you might be familiar with this type of results. So this type of results often created by cross-domain GANs. So you can change one photo using another photo styles. And those are all the traditional GANs that are majorly using images and text data, but none of them are good at generating tabular data, majorly because tabular data has a lot of continuous variables, and those traditional GANs had a challenge to process continuous variables in the tabular data. And therefore, today I'm going to introduce these three latest tabular GANs. But at this moment, let me see whether you guys have any question. And currently, I've already have seen some questions. So the first question is, where can we get this recording meeting session? Recording meeting session. I'm wondering, Ira, do you know what?
Yes, the recording will be shared over email tomorrow. The recording of this webinar, they're asking.
Great. And the second question is possible. Oh, the second question is the same. They are asking whether you can get the recording. Yes, you will get the recordings through email. Yes, tomorrow. Okay, so the next question is, what is GAN and what is DC GAN? Okay, so GAN is called generative adversarial networks. And you can just consider this type of networks, neural networks, are often used to generate fake data. Either it can be fake images, fake text, all kinds of fake data. So that's why previously when I was showing you the fake images of Taylor Swift and other celebrities, all kinds of fake data can be generated through GANs. And the DC GAN is the most fundamental algorithm in GAN. It has the most fundamental architecture. So later, all kinds of GANs are built their architecture upon DC GAN. And the next question is, doesn't the generator need to have different loss function from that of the discriminator? Yeah, you can have different loss function. In some of the architecture, they use different loss functions. Okay, so is there any other question? Okay, if there's no more question, then I'm going to keep talking about details on tabular GANs. And we are going to start with CT-GAN. So CT-GAN is like the vanilla version of all the tabular GANs. Later, a lot of more complex tabular GANs were built upon this fundamental. So now let's briefly understand how does it work. CT-GAN is a paper that's published in 2019, and this is its architecture. As you can see, it still has those fundamentals used in DC GAN, which you can see the discriminator and the generator. Comparing with DC GAN, CT GAN only made two kinds of major changes in the architecture. Let's break it down. So the first major change is called mode-specific normalization. So this solution is trying to handle continuous variables. So by using mode-specific normalization, the continuous variables will be converted into vector encoded format, so that the neural network architecture will be able to process the continuous variables. If you compare continuous variables with discrete variables, so in your tabular data, discrete variables can be converted into one-hot encoded format directly, and therefore the data can be processed by neural networks directly. This is very straightforward. But traditionally, in those traditional GANs, continuous variable could not apply one-hot encoding on them, and therefore mode-specific normalization had been introduced in order to convert the continuous variable into vector encoded format. If you want to understand the details on how does mode-specific normalization work, we can talk about it in detail at the end of this talk. I'm going to show you details on how does it work. At this moment, you just need to know each continuous variable is represented by alpha and beta here. Alpha is a normalized value, and the beta is a one-hot encoded vector. So by concatenating these two things, it can represent the values in continuous variables in vector format, so that the continuous variables can be processed by the GANs. And this is the central idea of tabular GANs. Another major change is called train by sample and conditional vector. This solution is majorly trying to address the data imbalance problem in discrete variables. So traditionally, if your discrete variable has a data imbalance issue, then it's likely that the minority values won't be represented in the generator's output. This can affect generator's output fairness. It can also affect the output accuracy. Therefore, this solution came up is trying to address this weakness. So train by sample, it means every unique value in your discrete variable will have some examples represented in the data sample that used to train the model. A conditional vector, it means when creating this data sample, it's using the real data examples to put in the sample. And that's all the architecture for CT-GAN. Here is how do we write the code to use the CT-GAN. As you can see, it's just a one line of code. It's very easy to use. And here, I just used the one parameters to tune. And this was good enough for me. At the same time, I provided the link where you can find all the parameters you can tune in CT-GAN. Also, I provided a page that tells you how to install the library. In fact, for CT-GAN, you just need to use pip install. So it's very easy to install and very easy to use. Now we are going to talk about the next tabular GAN, which is called CTAB GAN Plus. Okay, at this moment, is there any question? Let me see. I saw some written question. So how's the output if the GANs used to generating healthcare image data like CT scan or X-ray? This health image data. Oh, so to generate image data, CT scan. Oh, okay. There are good GANs used to generate the healthcare image data, but today we are focusing on talking about tabular data. So if you want to check GANs used for healthcare image data, feel free to do some research. Okay, and is there any other question at this moment? Okay, if there's no, then I'm going to talk about CTAB GAN Plus. So this CTAB GAN Plus was published in 2022, and this is its architecture. As you can see, this architecture looks quite similar to CT-GAN, but it just has made some improvement upon CT-GAN. So first of all, as you can see here, it has added an auxiliary estimator. So This method had been widely used in different neural network architectures, especially in GANs. The assumption behind is by adding this extra estimator, it can improve the performance of discriminator and finally can improve the output quality from the generator. And this auxiliary estimator, it can be a classifier or it can be a regressor. It depends on what does your discriminator wants. And the next major change appeared in feature encoder. So as you can see in feature encoder here, there are 3 components. The first component is still mode-specific normalization. This is exactly the same as what we just saw in TGAN, and this solution is used to convert continuous variables into encoded vector format so that the value can be processed by the neural network. And the second feature encoder is using log transform. This method is majorly to deal with the long-tailed numerical variables. So when your numerical variable has a very long tail, then it became challenging for mode-specific normalization to normalize your data. Therefore, if you apply log transform to the variable first, it can shorten the distance between the long tail and the rest of the data. So in this way, it became easier to process the data by mode-specific normalization. And the general transform, this is a method that had been that's trying to convert your encoded variable into value range between -1 and 1. So by doing this, it allows the encoded data to be directly compatible with the output of the tanh activation function used by the generator. And this is the code on how to use CTAB GAN+. As you can see, the code is still very simple, same as how you are using machine learning models. Just customize some parameters in the model. It also allows you to customize which columns you want to apply log transform, which columns you want to apply general transform, or other kinds of feature encoder. If you don't customize these values, the algorithm will make the decisions for you directly. And here I've also provided the parameter list that you can tune when you are using CTAB GAN+, as well as the installation process. And now we are going to talk about test GAN. Before we talk about test GAN, is there any question? Let me say, I saw there are some new questions. Okay. Does train by sample completely replicate the distributions of each unique variable, or is the distribution generated by the GAN different from that found in the original data? Yeah, that's a good question. So it's not completely replicate the original distribution. You can consider this is like undersampling the majority values and oversampling the minority values. The purpose of train by sample is trying to make sure each unique value in the discrete variable will be represented in this sample so that the generator can learn all kinds of unique values that appeared in the discrete variable. So the distribution is definitely different from the original data. And the next question, can it generate more complex table with nested columns or nested rows? That's a good question. Nested columns and nested rows. So I'm wondering, what do you mean by nested columns? Do you mean, I mean the nested columns, you mean it's in dictionary format, JSON format? or what kind of format? Oh, it seems that I'm not able to hear from you guys. I think so. If your nested values can be converted into discrete variables, or it can be converted into continuous variables, then it can still be generated by it can still be processed by tabular GANs. But currently, otherwise, currently maybe tabular GANs won't be able to generate nested structure automatically. Okay, let me see the next question. Will you be sharing the data bank presentation links? Yes. So after today's talk, I'm going to share the links to Ira, and she's going to send the email to all of you with all the links. Where is CTGAN used? Yes, so CTGAN currently it's already being widely used in generating tabular GANs. If you even when you are working in the industry, if you want to generate a synthetic tabular GANs, then you can start with CTGAN. And this library is built by MIT. So not only it has been widely used in it has been widely referred in a lot of latest research papers, but it had already been used. And later I'm going to show you some experiments on how can we apply CTGAN for industry use case. Next question. Not to take in, is this being recorded, and what is the link for previous recordings, please? Okay, so according to Ira, every time after the talk, you will get an email to show you the links of the recording and other links of the resources. Okay, let me see. Next question. How does data generation with GAN comparable to SMOT and its variants in terms of data quality? For some use cases, SMOT variants can really suffer if the class labels are very close or overlapping. Yeah, that's also an interesting question. So currently the difference, one of the difference is when you are using GAN, I'm going to show you the example later. It can generate categorical data, looks quite similar to your original data automatically, so you don't need to do any data pre-processing. At the same time, when it comes to the structure, tabular GANs has its architecture, which is related to GANs architecture, which is different from SMOT. And when you are saying that SMOT variants that suffer when class labels are very close, this really depends on different data cases. And in my experiments later, I'm going to show you an example. Might be related. Okay, next question. Let me see. A column has two columns within. Oh, okay. So I guess you just added that. So nested column with a column with two columns in it. Okay. So currently, tabular. These three tabular GANs I'm introducing cannot handle nested columns automatically. Next question, can you generate data within multi-label correlation? A multi-table with a multi-table correlation. With a multi-table correlation, you mean multiple tables, or there's a correlation within the data, or there's a multi-correlation within the data? So I assume that your question means whether it can address the data correlation in the data. So GAN, I'm going to talk about. It can consider data correlation and data interaction when it's trying to generate the synthetic data. Okay, next question is how to access the recording. So you are going to get the recording through email tomorrow. And next question, can the TGAN and GAN be used to generate data to train large language model? Language model, you can, but large language model, currently, I'm not sure, I haven't tried that. But there are other, but if you want to train large language models, you can use specific models for that purpose. That will be better. Because TGAN and GAN, these are majorly focusing on tabular data, which are still has most of the tabular data contains numerical continuous variables and some discrete variables. Is there a method for tracking generated data back to the originating example? Yes. So what you can do is when you you don't you can just keep the data index the same. So then for the same index of data, you can just track back. But normally when you are using tabular data, it will totally change all the values. So I personally don't see that you have to track back to the original example. But if you really want to do it. It just check the data index. It's the same. Okay. Next question. When we use synthetic data for model training, how is it managed in automated model circumstance? We always retrain the model on newly generated synthetic data. And what about the evaluation metrics do we use? Okay, so I'm going to talk about evaluation metrics in the experiments stage. And there I'm going to show you more details. Okay, I'm still seeing more and more questions had been noted down. So now I'm going to talk about, keep talking about my presentation, and I will address the later questions at the end. Okay, so now let's talk about how does TGAN works. So TGAN is a paper that's published in 2023. This is its overall architecture. And it looks quite different from the previous two architecture you just saw, but in fact, this one contains a lot of similarities. So now let's break it down. First of all, there are multiple generators. Each orange square here is a generator. Multiple generators in this architecture, and they are getting the same noise data as the data input. Each generator is responsible for generating only one variable, only one of the variables in your data. At the same time, all these generators are connected sequentially. And when previous generator has generated its synthetic variable, it will pass the output to the generator and to the next generator. And finally, at the end, the last generator is going to pass all the generated synthetic variables to the discriminator. At the same time, you can see each generator has a shortcut connection to the discriminator. So now I want to ask you guys a question, which is here, why it has this type of shortcut connection between each generator and the discriminator? Why not just have the last generator connected to the discriminator? Considering you guys cannot talk, so I'm going to answer this question myself. So previously, I have been checking the whole paper very carefully, and I didn't find the reason, but I have an assumption. So the shortcut connection had been used in a lot of neural network architectures. So as you can see in these two examples, these are the example had been used in RESTnet. So the way shortcut connections work is rather than having your last node connect to your target component at the end, you can have some nodes in the middle to connect to your target component at the end. So by doing this, it can reduce the communication hierarchy in your neural networks. And this can reduce gradient vanishing from happening. Because when you have more layers in your neural network, it becomes more risky to have gradient vanishing. So that's why by adding these shortcut connections, it can remove the communication hierarchy and can reduce gradient vanishing from happening. At the same time, the purple square here represents auxiliary estimator. So we just saw auxiliary estimator in the previous tabular GAN. And here, each generator has its own auxiliary estimator. The purpose of this auxiliary estimator is to predict the variable that its generator is trying to generate. And in order to predict this each variable, each auxiliary estimator is trained on the rest of the variables in your data. At the same time, all of these auxiliary estimator are light GBM models. So by using light GBM, it can handle categorical features automatically, so you don't need to do any data pre-processing. So that's all the architecture of GAN. We had broken down the whole architecture. And this is the code on how to use GAN. As you can see, from data loading to getting data output, there are just a few lines of code. It's still very easy to use GAN. And here I've also provided the parameters to tune as well as the installation process. So now I'm going to talk about experiments, details, and some findings. So maybe in this section, I might be able to cover some of your previous questions. So let's talk about details first. When I was trying to do the experiments, I was trying to mimic the real use case when we are using synthetic data in the industry. So one of the major use cases is rather than training our machine learning model on the real data, if we want to protect the data privacy, we can train our model on the synthetic data. This definitely means it will sacrifice the model performance. But if the synthetic data has a good quality, that allows us to get some decent machine learning performance, then you train our machine learning model on the synthetic data is enough. And the experiments I'm going to show today is majorly to show how can we train the model using synthetic data and their results. So the data I'm using here looks like bank's data. I got this data from Kaggle. It's customer deposit data. So each record is recording customer data, and the target variable is a binary variable indicating whether the customer has deposit or not. This is similar to the bank's data, but in the bank we have much more complex data structure. In this data set, there are more than 11K records. There are 7 numerical features and 9 categorical features. The target variable is also quite balanced. There are around 50% positive class and 50% negative class. When I was splitting train test data, I was using 70% training data and 25% testing data. So this is an example of generated synthetic data. What does it look like? So as you can see, the generated synthetic data, in the example, it looks just quite similar to the real data. Almost cannot tell the difference. First of all, evaluation metrics. So when I'm trying to evaluate the generated synthetic data quality, first of all, I just wanted to check the generated data distribution, comparing with the real data distribution for each variable. So here, for numerical features, I was using PSI score to compare their distribution differences. And for categorical features, I was using GS distance to compare the feature distribution differences. But the evaluation metrics here is not the major metrics I'm using. The major evaluation metrics are collected in this table. Because at the end, what we really care about is even if the distributions can have larger difference, but if the model we trained on the synthetic data can get acceptable results, then that's good enough. So here, the way this experiments work is here, as you can see, I have different ensemble models. There are like GBM, XGBoost, CatBoost, these boosting models. I've also used the stacking. And the benchmark is I'm using the models to train on the real data and evaluate. And this performance is showing the evaluation performance on the testing data. As we just mentioned, the real data was using 70% of data as the training data. When I was generating synthetic data using each tabular GANs, they are generating the same size of training data. And here I want to emphasize the synthetic data. They are only the synthetic data here. They are only used to generate the training data. So later, when we are comparing the model performance, the models trained on synthetic data will still evaluate on the real testing data. So all the testing data here are the same. This also aligns with how we are using synthetic data in the industry. So we normally train our model on the synthetic data, and then the model will be used to forecast on the real test data in the future. And when I am comparing the performance of these tabular GANs, first of all, I want to check the computational efficiency, which is in order to generate the same size of training data, how long it will take each tabular GAN to execute. For CTGAN here, it took 17 minutes. For CTAB GAN Plus, it took around 30 minutes. And for CAST-GAN, it took 15 minutes. Next, I'm using LightGBM to evaluate the model performance. And also all the models here, I'm using optimized model performance, because in the industry, we often need to tune our model in order to choose the optimized model as the final solution. So as you can see here, CAST-GAN got the best performance, best AUC, best AVP for this data, but the performance are very low. It's just around 0.5. It's a very low performance. Later, I've tried XGBoost. And here I no longer use CTAB GAN Plus. It's because CTAB GAN Plus got the lowest performance in LightGBM. Also took a very long time to generate the training data. So I thought now I only need to compare CTGAN and CAST-GAN to see which one works better. So again, in XGBoost, in CatBoost, cast GAN still works better, but the performance are always below 0.6, still a low performance. Later, I've also tried stacking. The stacking here had stacked all these three optimized ensemble models in the stacking. In this example, in this experiment, CT GAN worked better, but the performance is still very low. So later, I made some minor adjustment, and I call this method as ASDGP method. Only by doing this minor adjustment, the performance had improved more than 20%. And now both AUC and AVP became more than 0.6. In some cases, if you only need a simple model, this type of performance is acceptable. And today, this is the tip I want to share with you guys on what kind of minor change we can do that can get you better model performance if in the future you also need to use train your model on the synthetic data. So I was majorly checking the feature distribution because previously when checking all this performance, I was thinking the major reason that the model all got a very low performance, maybe it's because the generated feature had a confused positive class and a negative class in the data. Therefore, in order to validate my assumption, I want to check the feature distribution, especially those most important features distribution in positive class and the negative class. I want to see whether I want to see the comparison. At the same time, I'm also making the comparison between real data and the synthetic data. So as you can see here, in the first row is showing two top features. The green data is the real data, and the red data is the synthetic data. If you just look at the positive class distribution, you cannot get much insight. But when you look at the negative class distribution, there's something interesting that's showing here. So if we just look at the green data for each feature between their positive class and the negative class, we can see there are larger difference between positive class and negative class. And maybe because of this difference in the two classes, it helps the model to distinguish the two classes better. But if we look at the red data, the synthetic data in negative class, obviously it has more overlap with the positive class, which means in our generated synthetic data, the generated positive class and the generated negative class are more mixed together. Therefore, the data has confused the model, and the model performance stay very low. Therefore, I was thinking, maybe I can just change the data generation process when we are generating the synthetic data. And AES-DGP is a name I made up, which means adjusted synthetic data generation process. So just to generate the data generation process, I was wondering whether it can improve the model performance. And the way I was doing is to generate synthetic training data for each class separately. In this way, I was hoping the generated positive class and generated synthetic negative class can have their distribution closer to the real data distribution, and therefore we'll be able to better distinguish between the real data between the two classes. So finally, only by doing this minor adjustment, the performance improved 20%. And also, there's no data leaking or cheating here, because when you are generating your training data, you always know the real labels, which is positive, which is negative. So there's no cheating or data leaking here. And that's all for today's talk. And here I provided the written tutorial, which includes all the detailed code. All the code is written in notebooks, so you can see all the experiments in detail. And also it includes all the detailed explanation, as well as installation, all those things. Okay, so we are already 1 o'clock now. So let me, okay, I'm seeing a lot of questions here. Let me answer these questions. So the next question, is the data generated accurate? Are there no mistake in the data? Yeah, as you can see, currently the tabular GANs are still improving. If you look at all those tabular GANs papers, all the performance, they are showing are very low. And what you are seeing in my experiment here, the performance here are already much higher than what you can see in those tabular papers, tabular GANs papers. So I would say the data generated not accurate. And therefore, if we need to train the model on the synthetic data, it will definitely sacrifice the model performance. The next question, are there any performance constraints or advantage between various flavors of tabular data? Performance constraints. Performance constraints, it can be, for example, CTAB GAN plus, it took a longer time to generate the data, and the performance is not good enough. And the advantages, it can be, for example, CAST-GAN. The architecture of CAST-GAN allows you, the architecture of CAST-GAN here, because the generators are selected sequentially, by having this type of cascading architecture, it's able to consider the correlation and the interactions between features. So that's one of the advantages CAST-GAN have. Next question, can this be used for continuous target variable? Yes. So these methods can be used in any tabular data. Next question, is the data interlinked? I mean, are the rows and columns are interlinked? Maybe not. I don't know what does interlinked mean, but maybe not. If you mean interaction, if you mean feature interaction, there can be data interaction, and algorithms such as CAST-GAN is able to handle the data interaction. Next question, multi-tables, for example, 2 tables with different information, such as demographic data and health data, and they are linked by primary key. Can it generate synthetic data using that? So the tabular data will just generate the synthetic data for each table separately. Next question, how does it ensure distribution replication? Okay, so I guess maybe this is related to previous question. There's distribution replication. There's yeah, the distribution will have some change through their methods, but it will just try to be able to generate all kinds of values that appeared in the data. And what is the reason for sequential connection in CAST-GAN? Is it to simulate function for joint probability? So the major purpose for sequential connection here, according to the author of the paper, they are trying to use this structure to take into feature connection and feature correlation into consideration. Okay, next question. Oh, there's so many questions. How does GAN ensure distribution replication? GAN. So by using auxiliary estimator. So when you are using auxiliary estimator, it will try to predict the variables using the rest of variables. Through this process, it will be able to represent the original data distribution. It's similar like how you are using light GBM, trying to forecast the value. Okay, next question. Noise generator makes sense, but how does Gen AI generate synthetic data? Okay, this one I'll skip because today we are focusing on tabular data. Next question. For GAN, if each generator is trained on only one feature, how does the discriminator process or understand the correlation and the dependency between different features? That's a good question. So it's because each generator is still getting previous generators' data input as their input. And therefore, this means the later generators is getting not only noise data, but also previous generators' data as its data input, which already has the data interaction and data dependency information in it. So next question, GAN seems to be more dependent on the data hierarchy. Does this mean that errors in the data propagate easier and can contaminate the generated synthetic data? I don't think so. It's because it also has auxiliary estimator had been added for each generator in order to ensure its quality. And therefore, at the end, when you are seeing the experiments, GAN has better performance than other tabular GANs. Okay, next question. What is AOC and AVP? So AOC is just in machine learning. When you are using AOC, ROC, here it's using the AOC value. And the AVP is average precision score. It considers both precision and specificity. Okay, recording will be available tomorrow in the email. What is your level of confidence in using synthetic data for training a model, and what can we do to reduce the risks of using biased and non-real world scenarios? I think to do this, I think from now here, there are still more things you can do. As you can see here, I provided the whole set of parameters that people can tune. So this is data scientist's job, that we need to tune the parameters and find the way that works better for our specific data case. So better tune the parameters, and it also depends on use case. In some of the use case, if your model reaches to around 60% or 70% AUC or AVP, that's good enough. Then I'm confident with that. But if you need to reach to 80%, 90% AUC or AVP at this moment, I'm not very confident on that. Okay, that's the two questions. Among all is the best traditional GAN used for generating synthetic data? So traditional GAN, it depends on what synthetic you mean. If it's synthetic tabular data, none of those traditional GANs are good at that. If it's synthetic video or text data, there are different GANs. It's also used for different purpose. I think it's better for you to do some research, because different GANs are really used for different purpose. But you can check the latest GANs, then they may be more advanced. Okay, next question. The performance metrics of the synthetic data is worse considering the raw data. How does the training model with the data add any value? Oh, so the major value is to protect the data privacy. So when you are in domains like healthcare or even in the banking, sometimes you don't want to you want to protect the privacy, and you don't want to use the real data, and therefore at this time you train your model on the synthetic data. This will definitely sacrifice the model performance, but it's better than having no model. So that's the value. Major value is protect the data privacy, and it can be used in ethical AI. And therefore, when you are train your model on synthetic data, next major thing you need to do is to tune the parameters and try to improve the performance. Yeah, so that's all. And thank you for coming. Sorry for running out of time, and thank you for coming today. And tomorrow, Ira is going to send you the links.